Welcome to this explainer. You know, when we picture volcanic destruction, our minds usually jump straight to those crazy Hollywood blockbusters. We're thinking towering plumes of ash blotting out the sun, earth-shattering explosions, and rivers of glowing red lava just consuming everything in sight. But what if I told you that violent, fiery eruptions aren't the only or even the most surprising way a volcano can utterly destroy a landscape? It's a bit of a terrifying paradigm shift, honestly, but it's totally true. Volcanic landslides can happen without a single eruption. We tend to view mountains as these permanent, unmoving anchors in the landscape that are going to outlast us all. But in reality, gravity, water, and deep structural decay are these incredibly dangerous, invisible threats. They can literally bring a supposedly sleeping mountain to its knees at any given moment. Which brings us to a pretty huge question. So, what makes a massive solid rock volcano just fall apart? Today, we're going to reframe how you look at these towering peaks. They aren't just solid chunks of stone. They're incredibly complex, shifting structures, constantly fighting a losing battle against the forces of nature. So let's dive into the science of mass movements and find out why these mountains are essentially ticking time bombs. All right, let's jump straight into part one, rotting from the inside. To really understand how a mountain collapses, we actually have to start small, very small. We need to look at the invisible internal pressures building way deep inside the mountain. It all begins with a process called hydrothermal alteration. Deep underground, magma releases volcanic gases that dissolve right into the groundwater, creating this boiling, highly acidic fluid that relentlessly circulates through the mountain's core. Over time, this hot acid literally eats away at the rigid volcanic minerals, transforming solid rock into soft, slippery clay. Think of it kind of like a severe cavity hollowing out a tooth. On the outside, it looks totally fine and sturdy, but inside, the mountain is basically rotting away. And this is where things get genuinely sketchy. Recent lab data from the U.S. Geological Survey on rocks from places like Chaos Crags out in California reveals a pretty wild statistic. This alteration process can reduce a rock's permeability by 4 orders of magnitude. That is 10,000 times. As the rock breaks down, precipitated minerals fill the microscopic cracks and seal them completely shut. This traps all those fluids and turns the inside of the volcano into a highly pressurized, unstable trap. It's essentially a giant geological pressure cooker, just waiting to blow. Which perfectly sets up part 2, the push of magma. So we now have this rotting, highly pressurized core. Now imagine the sheer physical stress of new, rising magma pushing aggressively against those newly weakened walls. The mountain is basically being attacked from the inside and from below all at once. We actually have real INSAR radar data overlaid with some really cool analog sandbox models tracking Anak Krakatau, a volcano in Indonesia that suffered a massive collapse back in December 2018. Satellites bouncing signals off the Earth proved that discrete magmatic intrusions, so magma aggressively shoving its way up, were physically pushing Anak Krakatau's frank outward long before it actually collapsed. The mountain wasn't just sitting there, it was quietly deforming and bulging for years before gravity finally took over. To put the scale of that into perspective, normally the flank was creeping down slope at a relatively slow 27 centimeters a year. But during a magmatic intrusion in early 2017, that deformation rapidly accelerated to nearly 150 centimeters per year. It's exactly like inflating a damaged balloon. The raw pressure of the magma is rapidly accelerating the structural failure, physically pushing that weakened rock right past its breaking point at terrifying speeds. Let's look at that breaking point in part 3, when mountains fall. Let's let the tension release for a second and step out from the microscopic level and satellite data to the terrifying macro event, the physical breaking of the mountain. How does this chain reaction actually play out? First, magma intrudes into the weakened edifice. Second, that intense pressure reactivates deep, weak fault lines, acting like a slick geological slip and slide deep in the earth. Third, an entire sector or flank of the volcano physically detaches from the main body. And finally, gravity takes over, giving us a massive, chaotic debris avalanche plunging down the slopes. The scale of these avalanches is just mind-blowing. They possess so much sheer velocity and momentum that they can surge right over massive hills and cross entire valley divides. Back in 1792, a landslide off Mount Mayuyama in Japan slammed straight into the Ariake Sea. It generated a massive tsunami that tragically killed nearly 15,000 people.
You see, the mountain collapsing is often just the initial trigger for these devastating secondary hazards that spread the destruction miles and miles away. This really highlights a crucial contrast. We spend all our time worrying about the classic eruptive hazards, your lava flows, choking ashfall, toxic gases. But gravity-driven mass movement hazards, like debris avalanches and landslides, can be just as deadly, if not more so. Why? Because they can happen with literally zero warning, and incredibly, even without a primary eruption to sound the alarm. 1 minute the mountain is there, and the next, it's racing towards you.
So what happens after the collapse? That brings us to part 4, rivers of concrete. Enter the lahar. That's an Indonesian term for what happens when these massive volcanic landslides meet water, and it is truly the stuff of absolute nightmares. When the mountain falls apart, the danger is honestly just beginning. There's a powerful description from the USGS that hits the nail on the head. A moving lahar looks like a rolling slurry of wet concrete. Because of the steep slopes, these insanely heavy slurries can reach speeds up to 120 miles per hour. They don't just flow over things like a normal flood, they crush, abrade, and bury absolutely everything. Imagine a wall of fast-moving cement just effortlessly tearing concrete bridges off their foundations.
But the wildest part? These lahars don't just stay one size. Kind of like a snowball rolling downhill, as they rush downstream, they can grow to more than 10 times their initial volume. They do this by just consuming everything in their path: loose rocks, soil, vegetation, buildings, even those bridges they just destroyed. A relatively small slide at the peak can become a monstrous, unstoppable flood carrying house-sized boulders by the time it reaches a town in the valley. And looking at the triggers, you realize just how easily these can start. It doesn't take a massive explosion. We're talking melting snow and ice from a hot pyroclastic flow, crater lakes suddenly bursting, heavy rain falling on loose volcanic ash weeks after an eruption, or just a landslide of wet, altered rock entering a river valley. The environment around a tall volcano is just perfectly primed to turn into a deadly slurry at a moment's notice.
Okay, I know this sounds pretty grim, but there is good news. Let's get into part 5, predicting the collapse.
Scientists are actively fighting back against these disasters, and they aren't just waiting around for them to happen in the wild. To predict lahars, researchers actually run controlled experiments using a massive 310-foot-long debris flow flume. It's basically a giant, highly instrumented mudslide water park for geologists. The data they gather feeds into complex mathematical software called DCLAW. This lets them simulate fluidly flowing events and accurately forecast how a debris flow will travel across real-world terrain, which is absolutely crucial for designing warning systems and mapping out evacuation routes. And this really drives home the main takeaway of this explainer. Because these mountains are quite literally rotting from the inside out, and because magma pushing from below can rapidly speed up that failure, simply looking at the surface just isn't enough anymore. Tracking those subtle physical deformations with satellite radar and meticulously monitoring magma intrusions is our best and sometimes our only defense against catastrophe. We have to look past the stone and see the shifting engine inside. So we've seen how internal decay, rising magma, and water can combine to pull a mountain down in the blink of an eye, which leaves us with this final, kind of chilling thought to ponder. If volcanoes are silently shifting, deforming, and rotting from the inside out beneath our feet right now, which mountain is the world's next ticking time bomb?
Thanks for joining me on this one.